All right. So our next goal for the next few weeks is to define an invariant of topological spaces that we can use to show that two spaces are not homomorphic. So this will be a group that we assign to a topological space so that homeomorphic spaces have isomorphic groups. And we'll use this invariant to complete the classification of surfaces to show that the surfaces that we suspect are not homeomorphic are in fact not homomorphic. But this invariant is applicable in much more generality. And so we want to talk a little bit about the setting for this invariant, how it's going to be defined. And the key idea that's involved in the definition of this invariant is the notion of a homotopy. Okay, so what's a homotopy? So a homotopy is a way of continuously deforming one map into another one. So what do we mean? We have a map F from X to Y and another map G from X to Y. We want to continuously deform the map F to the map G. So more precisely, what does this mean? A homotopy is a map from X cross 0, 1 to Y that interpolates between F and G. So specifically, at the 0 level, capital F is equal to little f, and at the 1 level, capital F is equal to G. Another way that we write this often is to think about for each fixed t, we get a function from x to y. So that's f sub t of x is just given by capital F of xt. So if we do that, we note that f sub 0 of x is just equal to little f of x. Whereas f sub 1 is equal to g. So we can think about the family, this one parameter family of maps, f sub t, as interpolating between the map f and the map g. And continuity is captured by continuity of the map capital F. So when we have a homotopy from a map f to a map g, we'll say that f is homotopic to g, and we'll use this notation f with a little straight line and squiggly line, G. So in general, a homotopy is just a map from a space across an interval, usually the unit interval 0, 1, to some other space y. And just like before, we'll think about this as a one parameter family of maps parameterized by the unit interval I. We call that little f sub t, just like before. So okay, a little bit about homotopies. Maybe an example, if we look at maps into Euclidean space, Rn, any two maps are homotopic. So we can prove this explicitly by using what's called the straight line homotopy. So how does that go? So let me just write down a formula. Capital F of xt is 1 minus t little f of x plus t g of x. So that's a continuous map from x cross I into Rn. And what is this map really doing? So if you think about for each fixed x, and you think about the map as a function of t now, so t maps to f of xt, that's just the line segment from f of x to g of x. So maybe a little picture. Here are two maps f and g. Into R2, they map the circle into R2. And then if we think about this family of maps, the left sub t, so one parameter family of maps interpolating between f and g. And what we're doing is just we're sort of sliding the map f along the straight line segments to the map g. So this works in more generality. As long as the line segment between f of x and g of x lives inside of the, so for maps into subspace of Rn, as long as the line segment between f of x and g of x lives in that subspace, this gives you, there's a straight line homotopy. So for example, if y is a convex subspace of Rn, then any two maps are homotopic by this straight line homotopy because convexity exactly says that the line segment between any 2 points is in the space. All right, a refinement of this notion of homotopy. So if you have a subspace, a subspace of X, then a homotopy relative to A is just a homotopy that basically, so that all the maps agree on A. Okay, so the formula there, f of xt equals f of xs for all x in A and t and s and I, that just means that for each point x in A, all the maps f sub t of x, they're all the same. Okay, and the notation is similar. We write f naught f1 homotopic rel A. Rel A means relative to A. So as an example, back to the straight line homotopy, if you have two maps into Rn, and if f and g agree on A, that is f of x is g of x for every x in A, then the straight line homotopy is a homotopy relative to A. Why? Because remember that what is this straight line homotopy doing? You're connecting each point f of x to g of x by the straight line segment. Well, if f of x equals g of x, that straight line segment is a point. Okay, so another notion that's important here that I want to define. So these algebraic invariants, like I mentioned, we're going to assign a group to a space. And next semester, you're going to learn about homology and cohomology. These are also groups that you associate or vector spaces you can associate to a space. And it turns out that most of the time, these kinds of invariants they're unchanged, not just by homomorphism, but by a weaker kind of map called a homotopy equivalence. So a homotopy equivalence is a continuous map from a space x to a y, such that there's a map that goes the other direction from y to x. And instead of requiring that the compositions be equal to the identity, we just require that the compositions be homotopic to the identity. So such a map G is called a homotopy inverse. So if you like, a map is a homotopy equivalence if it has a homotopy inverse. So you can compose F and G in both orders and get maps homotopic to the identity on the respective spaces. As an example, if F is a homomorphism, then it's a homotopy equivalence. You just let the homotopy inverse be the actual inverse. If there exists a homotopy equivalence between x and y, then we say that x and y are homotopy equivalent, or we might sometimes say that they have the same homotopy type. And the notation is sort of similar to the notation for homotopic maps. So if you see x and y, and this symbol x squiggle bar y, that doesn't mean x and y are homotopic. That doesn't make sense because homotopy is a property of maps. What makes sense here is to say that they're homotopy equivalent, or they have the same homotopy type. Okay, a special case that comes up often is when your space is homotopy equivalent to a point. If you're homotopy equivalent to a point, the space is called contractible. So for example, Rn is contractible. Why? So let's construct a homotopy equivalence from Rn to a point. We'll take that point to be 0 in Rn. So what is the map? Well, there's only one map to a point. It's the constant map. And then the map from G, our map G from that point back into Rn is just going to be inclusion. Okay, so F composed with G, well, the domain and range of that is just the 1 point set 0. So clearly that map is the identity. If I go the other way, if I do G composed with F, so first I do F and then I include the origin back into Rn, well, that's really just the same thing as the map F. And so now we can think about F as a map from Rn to Rn, and we know any two maps are homotopic. So in particular, F is homotopic to the identity using the straight line homotopy. So this example illustrates an important feature. So we think about Rn here as, collapsing down to the origin. Okay, so to make this precise, we define something called a deformation retraction. So first, if we have a subspace, a retraction is just a continuous map from X to A, which is the identity on A. Okay, so we say that a retraction is a deformation retraction if that map R is homotopic rel A to the identity on X. Okay, so we collapse X down to A, And if that collapsing down to A is actually homotopic to the identity, think about doing the homotopy from the identity down to that collapse. So we're sort of down to that retraction. So we're sort of collapsing the whole space X down to A. So maybe we should be a little more careful here. Instead of writing R as homotopic to the identity, what we really mean is we have the inclusion of A into X, and the composition of the inclusion with the retraction is homotopic to the identity. Okay, so here that inclusion is the homotopy inverse of R. So that shows that whenever you have a deformation retraction of a space X onto a subspace Y, then that deformation retraction is in fact a homotopy equivalence. So the example up above of Rn being contractible, we found a deformation retraction of Rn to a point, namely the origin.